And we are live from the NI Lille headquarters in north of France. Hi everyone, my name is Stefan Scheck and I'm responsible at NI for this range of products that NFC, wireless charging and smart card is. I think we're going to spend a great time together. So in the next 40 minutes or so, we're going to learn about active load modulation test. We are trying to understand together why it is important, what is it critical to test. So we have prepared an agenda which is actually extremely simple and straight to the point. So we are going first to discuss about the signification of active load modulation, why is it useful, what we are going to do with this in order to make sure that the implementation is successful. Then we will look together at how NI can help you implementers, especially PCD manufacturers, to ensure that your product is going to work well with IQ load modulation enabled devices. And then we are going to take questions which you are going to ask us. So don't hesitate to ask us questions on the chat, and we will be happy to answer them. Also, one more note is that from a logistical standpoint, don't bother taking notes or screenshots from our presentation. After the presentation, we'll send you a link and you will be able to see it again and again and again for you to exactly understand what we were trying to say if we were not clear on the first view. So with that in mind, please allow me to introduce to you my colleague Olivier Connet, who is going to walk us through the mystery of active load modulation test. So Olivier, maybe you can introduce a little bit yourself for those who don't know you yet.
Sure, Stefan. Hello, everyone online. It's a pleasure to be with you today. At NI, I'm a hardware engineer, specialized in analog and digital signal processing, especially in contactless communication. I've worked on this subject for 10 years now, and last month I focused on active load modulation feature for our tools. In my spare time, I'm also a teacher for engineer school to educate the young generation about NFC.
So that's really great to have you with us today, Olivier. And actually, to get things started, please allow me to ask you a very simple question. There has been contactless smart cards for more than 20 years now, and we start to hear now about active load modulation test. So why is that?
Active load modulation is something which is coming since 10 years approximately, but I need to explain how it came to us. First, I need to introduce the usual NFC communication, the one we know from the smart card industry, contactless card, the cards we are used to have in our pockets. Those cards are based on a PCD, a reader, and a PACC card, so the card side, which communicate at a frequency of 13.56 using coils, using magnetic coupling between the reader and the card. And in this communication scheme, something particular is the energy is coming from the PCD. So the PCD is sending data and this frequency, the 13.56 magnetic field, to the PACC. The PACC, to respond, is load modulating this field. So the energy and the main frequency is coming from the PCD. In terms of wave shape, people who work on this domain are used to see those wave shapes on their scope. For example, here we have a type A communication with the reader side and the card response in type A, that's an ASK communication. And we have the communication on type B, which is slightly different on the reader side with an ASK with a less modulation depth. And the response of the PACC is by load modulation with a BPSK modulation. In terms of spectrum, what happens when we modulate those signals is a spectrum composed of a carrier and a subcarrier, which is the carrier divided by 16 for the bit rate of between 106 and 848. Of course, the signal is bit coded. For example, in type A, it's a Manchester bit coding. The subcarrier is modulated in on-off key or BPS key, type A or type B, and everything from the PACC point of view modulates the 13.56 megahertz carrier. So we find the carrier from the reader, and the PACC is making those two sidebands, lower sideband, upper sideband, separated by 847.5 kilohertz. Everything here is based on a magnetic coupling, which is using a certain size of coil. And of course, it's easy when we have an ID1 size of coil, the size of a credit card, for example. And everything has been designed with this size in mind. But of course, we have been seeing NFC communication from smartphones and smart objects. And the designers have been trying to implement NFC communication in many kinds of objects, and that's not really simple. Imagine to have you have to place a smart card antenna, a coil ID1 size inside of those objects. When it's a smartwatch, of course, it's completely impossible.
Yeah.
Of course, we have, if we reduce the size of the PACC, we reduce the operating range, and we increase the required field level, magnetic operating field level. In many implementation, of course, we have a lot of metal things. We have a battery, a screen, and things that reduce, again, the usability of the system. The idea is to help the PCD to understand the PICC by adding some signal into the PICC modulation. With some extra electronics, the PICC add an extra signal to push the data into the PCD. This is the active load modulation idea. Active load modulation have been experienced a long time ago, and quickly the ISO have standardized these battery-powered tags into the ISO 14443-2 contactless card standard, and that was the door opening to active load modulation. Of course, a few months later, they standardized also the test for those kind of things. That was the beginning of it, and all the tests are still moving until today. Because everything is, those standards are still moving until, for example, 2018 for 10373. How does it work practically? Not very complicated. We have the same scheme as before, except that the antenna are much smaller on the PICC side, and the PICC is now a transmitter. We have still a usual PCD transmitting the carrier and commands to the PICC, and the PICC have now on active load modulation to reproduce, to synthesize the sidebands to respond, to be understood by the PCD. The result is the antenna could be very small, and we can adjust the transmission to make sure that the PCD is understanding the message from the PICC. There is a catch. There is something difficult to do in that thing. The PICC has to respond as a non-active PICC. It means that the carrier have been, the sidebands needs, and the carrier has to be synchronized, perfectly synchronized to the PCD. And that's the trick to make active load modulation to work perfectly.
Okay, so I understand the goal of active load modulation is to facilitate the integration of NFC inside more complex devices, which have a battery, which have other radio enabled. So this is looking great, but it also looks to me there is a lot of burden on PCD maker. What do you think the people from the ecosystem in general think about active load modulation?
Depends on the position. For chipset manufacturers, it works. They have been very creative with many technical solutions to make it work. Device designers are happy with that because it's easy to implement NFC function into any device with low design constraints and low cost. Products made with active load modulation are perfectly compliant with all the standards. They are tested as perfect PICC. Reader manufacturers experienced some technical troubles. Some active load modulation designs have strange behavior. The problem lies into the synchronization of the PICC and the PCD carrier. There are many recipes to do that, more or less reliable. In brief, the PICC active modulation has been designed with some annoying behaviors, frequency and phase inaccuracy, or worse, the phase shift, phase drift. This is why the ISO introduced stringent limits into the active load modulation signal that PICC had to do, and also new testing method to make sure that the readers are able to understand this active load modulation.
Okay, so now I'm more and more convinced that it's going to probably be an issue for reader makers. Is there any possibility for them to do some tests to make sure that their design is going to be able to pass IQ load modulation enabled devices?
Yes, sure. ISO has designed this antenna, this active load modulation test PICC. This PICC is able to reproduce all to challenge the PCD and to create active load modulation signals to challenge the PCD and make sure that they are able to receive this kind of signal.
Get it. So I know very well actually the ISO 10373 part 6 test spec, and I know that there are already some reference PICCs which are defined. So how is this one different?
In fact, this PICC is active. It means this PICC is a transmitter. Compared to the passive one, this PICC has got some transmission capability. It's designed on the antenna side quite similarly to the passive test PICC. There is a coil to receive the PCD and to transmit the PCD to the testing device. On the other side, this PICC is able to send an RF signal to the PCD. It means that this PICC needs a power supply and needs a much more complex signal than the passive test PICC. We have to recreate all those subcarrier things.
Okay, so I understand it is quite different from the traditional reference PICC. But tell me, Olivier, is it going to replace the traditional reference PICC or is it going to be an addition?
No, the passive test PICC is still present in the ISO test. We still perform Hmin, Hmax waveform measurements with the passive test PICC. The active load modulation test PICC is only for the phase problems and to test for specific tests in the ISO library.
Okay, thank you. So I think it was really important to clarify this. It is going to be some additional test methods that will need to be played compared to the traditional ones which are currently enforced. So Olivier, please tell us more about how we are going to use this antenna. What will be the philosophy of test when we will use this antenna?
The test, we need to challenge the PCD with all the possible situations that can be encountered when reading an active load modulation PICC. Our test tool must recreate every active load modulation situation with many parameters. We need to create subcarrier abnormalities. We need to reproduce wrong phase lock, phase drift, and situation like this. ISO has defined many limits that we have to use and to generate to challenge the PCD, and we have to create a tool that is usable to do that.
Okay, but again, I know very well the ISO-6 test cases, and I know that using the reference PICC, we would, for example, challenge and define different value of physical parameters like the amplification, the modulation amplitude to challenge the reader. How is it going to be really different? I'm still not convinced.
For that, I need to explain how are those signals, those active load modulation signals. They are very different. Okay. Let's go back to school for that.
Okay, let's go to school now.
Here, I'm presenting a cosine signal. That's something which is electrically very common, and that's we can imagine the carrier of the PCD. On that carrier, we will have a modulation. On this example, we have the on-off key or O key modulation. So we see, we understand the modulated signal. Here we have three dots, 3 dash, and 3 dots. That's Morse code. Very simple. When we do this, when we multiply two cosine, we have something a little different. Remember, the PICC to PCD communication is based on a subcarrier. The subcarrier is a modulation of the carrier. And when we modulate, it means we multiply those carrier and subcarrier. When we multiply a carrier with a subcarrier at 847.5, we see two upper and lower sidebands appearing, just separated by 847.5 kilohertz. So modulation is just that. That's a multiplication between two carriers, one carrier and one subcarrier. When we have done that, we haven't made anything about the phase, and we can't distinguish both subcarriers. The amplitude is the same. For active load modulation, we need to do a little more. For that, we need some more mathematical tools.
More mathematical?
Yeah, sure. We need to enter into the complex number. We need to manipulate signal into the complex plane. It means we have a real part and imaginary part. Here we recognize the I and the Q signal. I means in phase, and Q means in quadrature of phase. That way, we can imagine that the carrier is a vector, which is here, and rotating all along the complex plane, and we can then manipulate amplitude and phase. Amplitude is the length of the vector, phase is the relative angle compared to the zero, to the reference. Changing phase and amplitude is simply multiplying with a complex number, and modulating is also multiplying with another carrier represented that way. Here we have made some addition of those vectors. We have added a carrier, an upper subcarrier, and a lower subcarrier. By just manipulating the angles and the length of the vectors, we can select and change every characteristics of both subcarriers, the carrier, phase, amplitude. Imagine the carrier is rotating that way in the complex plane at 13.56 megahertz. The upper subcarrier is rotating a little faster, and the lower subcarrier is rotating a little slower. This arrow is wrong, it's rotating on that direction. It's a little complicated to see that way, so I made some animation for you.
Let's take a look.
Here we have a carrier with two subcarriers added. Let's put that way. As we can see, we are here manipulating one carrier and two subcarriers. And what we see is the sum of it is getting smaller and bigger. And we have modulated the carrier with both those subcarriers. And we have created really an amplitude modulation. Nothing more. That's very simple. Those vectors are the signal, the carrier modulated. Here, I locked the carrier, so it's no more. The carrier is now our reference, so it's easier for us to see the signal, and we see the lower and upper subcarrier dancing by relation to the carrier. In black, I've put the sum vector that will be the final signal, the signal that the PCD will have to see and to demodulate, to understand. Here we have an ideal situation. Both subcarriers are perfectly the same amplitude, and the phase relation between the carrier and subcarrier is 0 degrees. That's an ideal situation that never exists in reality. The reality is a little like this, with, for example, the lower subcarrier and upper subcarrier of different size. And then the PCD will see some phase modulation as well as amplitude modulation. That's okay for most readers. That's a very common situation. Here we have another possible error. The phase of the subcarriers is bent by 45 degrees. That's also a common situation in active load modulation. It's where the PACC didn't catch perfectly the phase of the reader. That's one of the problems of active load modulation, and this could challenge some readers. Here we have another situation. It's a completely weird angles. It doesn't exist in reality, but we are able to manipulate the vector, so why not? It should be understandable by many readers.
So this kind of thing is legal.
This kind of thing is legal.
Okay.
Here we have made something different. We have only one subcarrier. One subcarrier is giving a perfect circle, and we still have phase modulation and amplitude modulation. And I can assure you that most readers will understand this. Of course, it's out of ISO standard. Here we have another situation that is present into the ISO test because it exists in the reality. We have another error from the PACC, the active load modulation PACC. In that situation, the PACC reference frequency is different from the PCD carrier frequency. There is a frequency error, and the consequence is the phase of the modulation is drifting in time from the beginning to the end of the frame. So we see that the global angle of the modulation is turning around.
So here we see a lot of vectors, and I'm sure one of my older math teachers would be proud to see that I'm finally using what they were struggling so much to teach me when I was young, not too long ago, hopefully. But Olivier, those vectors are great, but I believe what I can see. Do you have anything to show about what it looks like in the air?
Before that, I've made some simulation because I needed to implement this into MP500, for example. And before to make sure that I was correctly manipulating the vectors, I needed to make some simulation to make sure I was doing right. For example, here I created a carrier with 2 subcarriers, and that gives a type A data modulation that looks like what we've seen on the scope. It's a perfectly legal modulation, perfectly ISO. So I'm right with my subcarriers. Here, I shifted my subcarriers by 90 degrees. That's not ISO compliant normally. And of course, on the scope, we have something a little weird. We have shifted the modulation by 90 degrees. Here, I have only one subcarrier and some loading effect created by the PICC. So 2 spikes, and the other spikes are the modulation. And on the scope, we have a signal which is perfectly correct. And in fact, the PCD would be perfectly able to decode this signal as a normal PICC. If I put only 2 subcarriers and no loading effect, that's something which is perfectly legal and perfectly understood by any reader. Even if on the scope, the signal I sent by the PICC has something strange for us used to an NFC. Usually we have 4 bumps here, not 8 bumps. But it works perfectly. It's legal. The signal sent by this PICC is perfectly understood by the PCD. This is even more surprising. I send only 1 subcarrier. This will be understood by most readers, and on the signal sent by the PICC is flat. Very strange, but that's okay. In terms of signal, we have the necessary information.
A PCD is supposed to understand that?
Yes, perfectly.
Oh, okay.
In here, I went further. I created my FPGA, and in this FPGA, those are simulations, and these are on the top type A PICC modulation, type A106, and on the bottom type B modulation. Type A is ASK, is OOK, in fact, for the subcarrier. And type B is BPSK. We see here the phase reversal at each bit change.
Okay. And I'm sure after developing your simulations, you must have done some real-life trials. So can you share a bit of your results?
Oh, yes, sure. That's something that I have done with a real reader. Using NP500 and my FPGA. So I completely generated the subcarriers with any angle, any amplitude, and I used an ISO tool, a tool made by present in the ISO 10373-6 standard, which is able with scope acquisition to analyze the signal of the PICC to verify certain parameters. And here we have the constellation diagrams. Constellation diagrams is the complex plane we have seen with our vectors. Constellation diagrams with this shape means the vector of the modulation have been doing this travel, starting by the red cross at the beginning of the frame and going to the modulating and unmodulating states all along the frame. Here we have both subcarriers at 0 degrees angle related to the PCD. Here we have, I've set the subcarriers on the MP500 at 45 degrees, both subcarriers, and the ISO tool is measuring 45 degrees. Here I set both subcarriers at 120 degrees. So we see the initial state is far away on that direction, and the modulation is doing that way. And here I experienced to set one subcarrier at 45 and the other at minus 45, which is completely weird for, as a situation. But as you can see, the travel of the signal is correct. And of course, this signal is understood by the PCD. It was perfectly understood by the PCD. In terms of temporal thing, here is the scope view of the signal generated by the MP500. And here is another analysis performed by the ISO tool to have the spectrum. On the first one, I put only both subcarriers and no loading effect, so I don't send a carrier. On the second one, I sent loading effect and both subcarriers also at a lower level. Here, I sent one subcarrier only. If you remember into the animation, it was making a circle, and the ISO tool was able to see this circle. The modulation started at the red cross and then turn around, and the tool and a reader would be able to understand the modulated and unmodulated signal all along a complete PACC frame. Here, I've made one subcarrier bigger than the other. The lower subcarrier is bigger, and instead of having an horizontal travel, we have an elliptical travel. This is understood by a reader. ISO fixed some limits into the discrepancy of the subcarrier level. Here, I made something a little more complicated. The ISO standard 10373-6 specify a phase drift. Phase drift, I told you, is when the PACC didn't catch perfectly the frequency of the PCD for some reasons, and it happens. And it introduced the frequency difference, introduced a phase drift all along from the beginning to the end of the PACC frame. The phase drift in that example is specified by the ISO on condition A1 here to 15 degrees, and the phase will shift from the beginning to the end from 0 to 15 degrees. Let's see the result on the ISO tool. On the average phase is going to from 0 approximately to 15 degrees. And here we have the phase error or a few fraction of degrees all along the frame. And on the constellation diagram, we see the initial state. The phase is 0 degrees at the beginning, so the modulation was perfectly horizontal. And as we progress into the frame, at the end of the frame, we have 15 degrees angle of modulation.
So Olivier, I think you must have had a lot of fun developing all of that.
That's right.
Yeah. So, dear viewer, for your information, all of those difficult conditions were generated using the MP500 TCL3 signal generator, the test antenna, which we just shown, so which is specific for active load modulation test. And we have used a set of API which were specially designed for active load modulation test, and which are available on top of the MP500 TCL3. So Olivier, can you tell us a little bit more about which you can achieve with those API?
Yes, of course. I set a lot of. I wanted this system to be completely parametric. All the parameters could be changed even further than the ISO test limits. We, for example, have to set the reference carrier phase. Reference carrier phase means we have to adjust, of course, the PACC PCD to the PCD carrier. So we have a parameter for that. We generally we make one recording of the communication to measure this phase, and we set the initial phase to have a perfect 0 so that we can start the test and proceed to all the tests required by the ISO. We can adjust, of course, loading effect, its amplitude, its phase. So that's the red vector here. We can adjust its phase completely independently, and we can adjust its amplitude, the length of the vector. Of course, we can adjust the lower and upper subcarrier separately in terms of phase and amplitude. finally, we can adjust, generate exactly the condition of the phase drift specified in ISO 10373-6. We can create the ISO condition. A1 and A2 and B1 and B2 are a condition where the phase drift is constant from the beginning to the end of the PICC frame. And A3 and A4 are a little more complicated. The phase drift is only when in tape A106, when the the carrier is present.
So not only can we generate the conditions which are defined in the test spec, but we can go above those conditions.
Right.
Okay. So this is really good to know because it allows actually our users to characterize the exact limits of what their own device can do. So above the API, I also want our viewers to know that we have developed automated tests, which makes it really easy to actually perform those complex tests that active load modulation is. And I would like to take you to a small demonstration that my good friends Angèle and Thierry have prepared for you.
Hi, I'm Angèle. I'm marketing manager for the NI NFC group, and I am with Thierry.
Hi, I'm software engineer for NI NFC group, and I'm working on IQLM for 5 months.
Can you tell us more about what we have here?
This is an automated test system for IQLM. We will verify the ability of this contactless reader to demodulate signal coming from the devices which IQLM is enabled.
Can you tell us more about the hardware that you use?
We have this robot arm. From test references required to perform the test at different positions. But here, for the sake of simplicity, we will stay at 2 cm above the surface of the radar. Then we have the CTS, which is the very well-known conformance tester used in the majority of conformance laboratory for NFC and EMVCO. This CTS is connected to an antenna. This antenna will be used to interact with the reader.
This is the new IQ Load Modulation antenna. Can you tell us more about it?
Sure. This is an ISO 10373-6 Class 1 reference PICC for active load modulation. This will emulate the signal coming from an IQLM device, and it supports various physical parameters adjustment. The test tool can modify the phase or the amplitude of both sidebands at plus or minus the subcarrier frequency.
This wire is a power supply?
Yes, in order to generate the adequate signal, this antenna needs its own power supply because generating the IQLM requires a quite significant amount of power.
How does the test procedure will look like?
We have an automated software which will take control of all hardware and perform tests as per the test specification requirement. Here we are going to do type B test. And just by one click of this button, I'm going to play more than 200 transactions with different combinations of the important physical parameters.
200? It's a lot. Where does it come from?
First, for equal amplitude of both sidebands, it executes the conformance for the phases between 0 and 360 degrees by step of 5 degrees. Then, it executed for different amplitude. Amplitude of lower sideband 20% lower than the amplitude of upper sideband. And then, amplitude of lower sideband 20% greater than the amplitude of upper sideband.
Thanks, Thierry. So indeed, here I see we are testing all values of the active load modulation phase with steps of 5 degrees. We make sure the scheduled transaction happens correctly before giving a pass verdict. If anything goes as unexpected, then we will report a fail or an inconclusive result. Here, we have a failed item. You can clearly see, besides the fail information, we tell at which stage of the transaction the error occurred. And we continue to test all possible parameter combinations, allowing PCD manufacturers to assess the exact behavior of their product.
Thank you, Thierry. As Olivier already explained you earlier, IQ load modulation is very complex, and Thierry's team is making it possible for you to test just in one click. Let's go back to Olivier and Stéphane.
The question was, do we think that really a lot of readers are going to fail active load modulation test? And Olivier was saying that
all the readers that have been designed with a simple signal processing doesn't like the IQ load modulation signal.
So it is going to be something critical for a reader maker. And one thing I was thinking, listening to you, Olivier, is that if they do not care about IQ load modulation test, then they should really, because it's going to be big,
right?
Really impactful. Okay. Another question which I have from Marco. Marco is asking us, what should I do in order to enable my MP500 to perform IQ load modulation test? So this is this one is easy. This one you will need to download from the online portal of micropros.ni.com the latest firmware for your MP500 TCX3. By doing this, you will have also access to the documentation that accompanies the new API, and you will be all set. There will be examples that will take you through programming all of those difficult test conditions, and you should be good to go. We have 2 minutes left, so we can take maybe one more, which is how do we do to actually catch the face on the PCD test? So Olivier.
There are many recipes to do that, and all the designer, the chipset designer, have their own way to do it. That's why IQ load modulation is something which is difficult and that must be tested. It's difficult because you have to listen carefully to the PCD, to synchronize to it, and to generate a signal, and then the PICC is deaf and cannot hear anymore the PCD and can lose the synchronization at this time.
Okay. So it comes always to the question, IQ load modulation test, it is going to be important. So it's critical now for all the implementers to think about what their strategy is going to be towards this new range of tests which will need to be performed. So I think we're going to close there. I don't see any additional questions arriving. So I think now it's time to say a big thank you to all of you who joined us for this webinar. We hope it was interesting for you. I know I learned a lot, so at least for me it was great. Again, don't hesitate to wait for a few seconds after we go on offline to take our survey. We have one more question from Menno. So Menno is asking us, does this apply to passive RFID technology? So Olivier, maybe you can help us on that?
No, passive is only classical two-sideband modulation. The active load modulation is designed for active things, I mean devices with a battery, with a small antenna, like smartwatches, telephones, and things like that.
But thank you for the question, Menno. It was great, I think, to give a crisp answer on that. So unless in the next 10 seconds new question arrive, we are going to say goodbye. So I was going to say, don't forget to take the survey. We are really wanting to learn from you about what you think about this session. If you have any ideas about future webinar. Yes, it was a bit complicated to understand this. This I can totally agree. It's a complex topic. And this is why we believe this kind of webinar can be valuable, because if we don't do that, I'm wondering who else is going to explain you about that. So I think it's time to say goodbye. So thank you very much again for joining us. So for Angèle, Olivier, Thierry, and myself, Stéphane, I want to say thank you, and hopefully we'll meet you soon on site or through webinar, depending on how the situation evolves. So bye bye, and wish you all a